morning everyone. I hope you are all doing well. My name is Dr. Amar Kumar De and I am excited to welcome you to today's lecture titled Frequency Modulation and Demodulation Techniques for the course Fundamental of Communication System and its Application. It's exciting to see so many of you joining us from different corners of the world. First and foremost, I want to extend a warm thanks for taking the time to be a part of this session. So, without further delay, let's move on to the topic titled Frequency Modulation and Demodulation Techniques. Before moving ahead, here's a quick overview of today's lecture titled Frequency Modulation and Demodulation Technique. Today, we are diving into the fascinating world of frequency modulation, commonly known as FM, and the technique used for its demodulation. Frequency modulation is a method of encoding the information by varying the frequency of a carrier wave. It plays a crucial role in radio broadcasting, telecommunication, and signal processing. By the end of this lecture, you will have a clear understanding of how frequency modulation works, its benefit, drawbacks, and different demodulation techniques. First of all, we will recall the basics of frequency modulation, its definition, mathematical equation. Moving on, we will discuss frequency demodulation. Then we will explore the advantages and disadvantages of frequency modulation. One of the key advantages of frequency modulation is its improved noise immunity. Frequency modulated signals are less susceptible to noise and interferences compared to amplitude modulated signal. Now, we will delve into the frequency generation techniques. There are two primary methods. First one is the direct FM generation and second one is the indirect FM generation. Having understood how the frequency modulated signals are generated, let's turn our attention to the frequency demodulation techniques. A common method is frequency discriminator. Then we will explore the types of frequency discriminators, including the slope detector, which uses a tuned circuit with a linear slope, and the phase locked loop PLL. Additionally, there is the ratio detector, which combines amplitude and frequency detector to offer improved noise immunity. After this, we will consider some practical applications of FM. Then we will explore the discriminators, including the slope detector, phase locked loop, and additionally the ratio detector, which combines amplitude and frequency detection to offer improved noise immunity. As we wrap up, we will acknowledge the challenges and future trends in FM technology. In short, frequency modulation is a robust and high quality modulation technique with a wide range of application. Today, we cover the basics of this FM, its advantages, disadvantages, methods of generation and demodulating FM signals, and its practical application. Understanding these concepts is a crucial for professional in telecommunication and signal processing. Let's begin with the basic concepts of FM modulation and demodulation technique. FM modulation is a method of encoding information in a carrier wave by varying the frequency of the wave. This technique is widely used in radio broadcast, telecommunication, and signal processing. By the end of this lecture, you should have a comprehensive understanding of how FM works, its advantages and disadvantages, the various techniques used for demodulating FM signals. Understanding the mathematical foundation of FM is essential for comprehending how this modulation techniques operates on theoretical level. We will cover the key formula an equation that describes the FM, provides you with a deeper insight into its functionality and application. So, in mathematical term, the FM signal can be represented as S of t is equal to AC cos 2 pi fct plus 2 pi kf integral m of t dt. Here S of t is the FM signal, AC is the amplitude of the carrier wave, Fc is the carrier, Kf is the frequency sensitivity of the modulator, and m of t is the modulating signal. The integral m of t dt represents the integral of modulating signals, which controls the frequency deviations of the carrier. While discussing the basics, one of the key parameter in FM is the frequency deviation. It is denoted by del f, which indicates the maximum departure of instantaneous frequency from the carrier frequency. The modulation index beta is defined as the ratio of the frequency derivatives of the modulating frequency FM. The modulation index determines the bandwidth of the FM signal. The Carson rule provides an estimates of FM signal bandwidth. It is given by B, bandwidth is equal to 2 times del f plus FM. This means that the modulation index increases, the bandwidth also increases, provides a higher quality signal, but requiring more spectrum space. To grasp the behavior of FM signal, let us discuss some advantages and disadvantages of frequency modulation. FM offers several advantages over amplitude modulation. The advantages are improved noise immunity. FM is less susceptible to noise and interferences compared to AM. Better sound quality. FM can provide high fidelity audio signal. Reduced signal distortion. Frequency variations are less affected by signal strength changes. Now, the disadvantages are larger bandwidth. FM require more bandwidth than AM, which can be a limitation in spectrum constrained environment. Complexity circuitry. FM systems are generally more complex and expensive to design and implement. Now, let us discuss the FM generation techniques. Generating a FM signal can be done through several methods. The two primary methods are, the first method is the direct frequency modulation, and the second method is the indirect frequency modulation. So, let us deal with the direct frequency modulation first. Direct frequency modulation, FM is generated by directly varying the frequency of the carrier waves in accordance with the amplitude of the input or modulating signal. This technique is fundamental in various communication systems, including radio broadcast, where it provides high quality audio transmissions and superior noise immunity. In this section, we will explore the principles of direct FM generation, the underlying technologies, and its practical implementation. So, the principle of direct frequency modulation generation. Direct frequency modulation generation involves directly controlling the frequency of the carrier waves with the modulating signal. The carrier frequency is varied in real time according to the instantaneous amplitude of the input signal. This process requires a device that can change its frequency based on input voltages or current, typically achieved using a voltage controlled oscillator, abbreviated as VCO. Recalling the mathematical representation of FM signal in direct FM generation, which was represented by S of t is equal to AC cos 2 pi fct plus 2 pi kf integral m of t dt. This is the fundamental equation. The frequency deviation is directly proportional to the amplitude of the modulating signal m of t. Now, the second important component is the voltage controlled oscillator VCO. The core component in direct frequency modulation generation is the voltage control oscillator. A VCO is an electronic oscillator whose oscillation frequencies is controlled by a voltage input. The frequency output of VCO is linear function of the input voltage, making it ideal for frequency modulation purpose. Now, if we discuss the operation of VCO, a VCO typically consists of a resonant circuit such as LC, inductor capacitor circuit, where the resonant frequency can be altered by varying the capacitance or inductance. In most modern VCOs, the capacitor is varied using a varactor diode. The varactor diode is a special type of diode whose capacitance changes with the applied reverse voltage. The relationship between input control voltage V and the output frequency F output of VCO can be expressed as F output is equal to F0 plus kV into the input voltage, where F0 is the nominal frequency of the VCO, kV is the voltage to frequency conversion factor, and V is the input controlled voltage. It is also represented as V in. When the modulating signal m of t is applied to the control voltage V in, the output frequency F out of the VCO varies accordingly, produce an FM signal. Now, there are few different types of VCOs available which can be used in direct frequency modulation generation, which includes LC VCO utilizing an LC resonant circuit where the capacitor is varied using a varactor diode. LC VCOs are commonly used in RF applications due to their high frequency stability and low phase noise. The next category of VCO is the crystal VCO. Uses a quartz crystal resonator to achieve high stability. Crystal VCOs are typically used in applications where frequency stability is critical, such as in communication systems and precision instruments. Ring oscillator VCO consisting of ring of inverters where the oscillation frequency is controlled by adjusting the supply voltage or the biasing current. Ring oscillator VCO are commonly used in integrated circuit due to their simplicity and ease of integration. Now, let us discuss some practical implementation of direct frequency modulation generation. To implement direct frequency modulation generation, several key components and considerations are required. This includes the VCO modulating signal condition and ensuring frequency stability and linearity. First, let us discuss about the modulating signal condition. M of t, the modulating signal, must be properly contained before applying to the VCO. This involves amplifying the signal to appropriate level and filtering it to remove the unwanted noise or harmonics. The conditional circuitry ensured that the modulating signal has the desired amplitude and frequency characteristics to produce the required frequency deviation in the VCO. The second consideration is the frequency stability and linearity. Frequency stability and linearity are critical parameters in direct FM generation. The stability of VCO's output frequency is influenced by the factor such as temperature variation, power supply fluctuations, and component aging. To achieve high stability, temperature compensated or temperature controlled VCOs are oftenly used. Linearity refers to the proportional relationship between the input control voltage and the output frequency. Non-linearities can cause distortion in the FM signal, leading to degrade the performance in the communication system. Linearization techniques such as pre-distortion of modulation signal or using feedback control loops are employed to ensure the linearity of the VCOs. Let us consider some designing examples. Consider a simple direct FM generation system using LC VCO. The designing steps will include, first of all, the VCO selection. Choose an LC VCO with the desired nominal frequency and a stable voltage to frequency conversion factor kV. Second is the modulating signal conditions. Designing an amplifier and filter circuit to condition the modulating signals ensures that the amplified signal has the appropriate amplitude to produce the required frequency deviations in the VCO. Temperature compensation. This implements the temperature compensation techniques to maintain frequency stability over varying environmental conditions. This can be achieved using temperature sensors and compensation circuits. Finally, testing and calibration. Test the system to verify the linearity and stability of FM signal. Calibrate the system if necessary to correct any non-linearities or drift in the output frequency. So, this is all about the designing of direct FM generation. Now, let us discuss some applications of direct FM generation. Direct FM generation is widely used in various applications due to its simplicity and effectiveness in producing high quality FM signals. Some noticeable applications includes FM radio broadcasting. Direct FM generation is used in FM radio transmissions to modulate audio signals onto a carrier wave for transmission. The VCO ensures that the carrier frequency varies in accordance with the audio signal, providing high fidelity sound to the listener. Next application is in wireless communication. Direct FM generation is employed in wireless communication system such as two-way radios and cordless phone to modulate voice or data signal for transmission. The robustness of FM against noise and interferences makes it ideal for this application. Television broadcasting. In analog television systems, direct FM generation is used to modulate the audio signals onto a carrier wave for transmission along the video signal. This ensures that the viewers receives high quality sound with television broadcast. One of the prominent application is in data transmission. FM modulation techniques includes direct FM generations are used in data transmission systems such as frequency shift keying FSK modems to ensure digital data onto a carrier wave for reliable communication. So, I would like to conclude this particular section of direct frequency modulation generation, which is a fundamental technique used in various communication systems to encode information onto a carrier wave by directly varying its frequency. The core component in direct FM generation is the voltage controlled oscillator, which produces a frequency output proportional to the input controlled voltage. Proper designing and implementation of direct FM generation system involves modulating signals conditions, ensuring frequency stability and linearity, and addressing practical considerations such as temperature compensations. So, direct FM generations offer several advantages including simplicity, effectiveness, and high quality signal productions, making it a perfect choice for applications such as FM radio broadcast, wireless communication, television broadcast and data transmission. Understanding this principle and practical aspects of direct FM generation is crucial for engineers and professionals involved in the designing and implementations of modern communication system. This explanation must have provided a comprehensive understanding of direct FM generation, its principle and practical considerations. Now let us move on to the second type of FM generation, that is the indirect FM generation. And indirect frequency modulation generation, also known as the Armstrong method, is a sophisticated technique used to create a frequency modulated signal. Unlike direct FM generation, which varies the frequency of the carrier directly, indirect FM generation starts with a narrowband FM signal and then converting it into a wideband FM signal. This method provides high stability and precision, making it ideal for applications such as broadcast radio and communication systems. Indirect FM generation involves several steps, including the use of the narrowband frequency modulator, frequency multiplier, a mixer, followed by another frequency multiplier. Let's delve into each steps in detail to understand the process. The first step in the indirect method is to generate a narrowband frequency modulated signal. This is typically achieved by using a direct frequency modulator. This modulator works by varying the carrier frequency in accordance with the modulating signal, as we discussed in our previous section, that is the direct frequency modulation technique. This modulation technique, this particular steps generally generate a narrowband FM signal with a smaller frequency deviation. A narrowband FM signal is characterized by having a small frequency deviation, meaning the frequency of the carrier signal do not deviate significantly from its original value. Initial narrowband FM signal serves as the starting point for the indirect FM generation process. Now, the second component in the indirect process is the frequency multiplier. Once we have the narrowband FM signal, the next step is to pass it through a frequency multiplier. A frequency multiplier is a circuit that increases the frequency of the input signal by a specific factor, say n. The primary function of the frequency multiplier is to increase the frequency deviation of the narrowband FM signal. If the narrowband FM signal has a frequency deviation of del f, passing it through a frequency multiplier with a multiplication factors of n will result in a frequency deviation of n into del f. This step effectively converts the narrowband FM into a wideband FM, which has a larger frequency deviation and better fidelity. Now, about this wideband FM signal. A wideband FM signal has a larger frequency deviation compared to that of a narrowband FM signal. This means that the carrier frequency varies more significantly, allowing for high quality transmissions of information, especially in audio broadcast application. Next important component is the mixer. After the frequency multiplier, the wideband FM signal is fed into a mixer. The mixer is a non-linear device that combines two signals, producing an output that includes the sum and the difference frequency of the input signal. The purpose of this mixer in the indirect FM generation is to shift the frequency of FM signal to the desired carrier frequency. This is achieved by combining the wideband FM signal with a stable carrier signal from a crystal oscillator. There is a frequency shift. The mixer output a frequency shifted wideband FM signal. This means that the FM signal is now centered around a new carrier frequency which is suitable for transmission. The frequency stability of the crystal oscillator ensures that the final FM signal maintain its inherent carrier frequency. The second frequency multiplier is now come into picture. the frequency shifted wideband FM signal is passed through the another frequency multiplier to achieve the final desired frequency deviation and carrier frequency. Similar to the first frequency multiplier, the second frequency multiplier further increases the frequency deviations of the FM signal. This step ensures that the FM signal meets the specific requirement for the transmission, such as the desired bandwidth and fidelity. The final FM signal, the final output of the second frequency multiplier is the final FM signal, which has the desired frequency deviations and carrier frequency. This signal is now ready to transmit over the air and through the communication system. So, in summary, the indirect method of FM generation uses a combination of narrowband FM signal, frequency multiplier, mixer to produce high fidelity, high quality FM signal. Now, some applications of indirect FM generation. The indirect FM generation is employed in various applications where high stability and precision controls over modulation process are required. Some noticeable applications include broadcast radio, communication systems. Indirect FM generations offer several advantages over direct FM generations, which includes frequency stability, control and precisions, and flexibility. While indirect FM generations offer many advantages, it also presents certain challenges and considerations. The first is the complexity. The system is more complex than the direct FM generation, required careful designing and integration of multiplier components. Component nonlinearity. Nonlinearity is a major issue when we talk of the frequency multiplier, which can introduce distortions, required additional signal conditioning. In conclusion, the indirect frequency modulation generation, also known as the Armstrong method, is a sophisticated technique that offers high stability and precision in generating FM signal. So, this is an example of this indirect method generation. Here, we have given with a wideband FM generator. The initial frequency is 200 kilohertz. The maximum frequency deviation is 25 kilohertz, and the final frequency deviation and the carrier frequency are to be obtained as 75 kilohertz and 102.4 megahertz respectively. Now, we assume that we already generated the FM signal using a narrowband FM signal. So, the inputs are the given input carrier frequency 200 kilohertz and the initial frequency deviation is 25 hertz. Passing it through a multiplier, we need a multiplication factor of around 3000 to reach the desired frequency deviation. But if we directly multiply it with the 3000, we will get the desired frequency deviations, but the final carrier shift. So, in order to maintain the final carrier, we need to introduce one more frequency multiplier and passing it through a mixer section. So, the modified model could be the narrowband FM, then a frequency multiplier stage 1, then there will be a mixer and then there will be the second frequency multiplier stage 2. If we calculate this factors, we need the two factors N1 and N2. On proper substitutions and assumptions, we can calculate, we can have them as N is equal to 30 and N2 is equal to 100. We need to calculate the crystal oscillator frequencies also, where the crystal oscillator frequency can be calculated using equation number 2. This is the final destinations required, and we see that by providing the input conditions, then the first multiplier stage, then a mixer stage followed by the last multiplier stage, we obtain the desired deviations along with the carrier frequency. So, this is an example. Now, the demodulation techniques. Now, let us discuss the FM demodulation technique. The demodulation process is extraction of the original modulating signals from the modulated carrier wave. The common FM demodulation techniques include the frequency discriminator. A frequency discriminator is a circuit that converts the frequency variations into amplitude variations, which can be processed to recover the original signals. There are various types of discriminators, which includes slope detector, a simple circuit that used a tuned circuit with a linear slope to convert the frequency changes into amplitude changes. Phase log loop (PLL), a more sophisticated approach that logs on the carrier frequency and tracks the variations to demodulate the signal accurately. Ratio detector. A ratio detector is a typical types of frequency discriminator that use a combination of amplitude and frequency detector to improve noise immunity. It produces an output signal that is less sensitive to amplitude variation, making it more robust against noise. In conclusion, the frequency modulation is a powerful technique that encodes the information in the carrier wave by varying its frequency. Understanding these concepts is crucial for anyone involved in the field of telecommunication and signal processing. Thus, we come to an end of today's lecture. I hope you found this lecture informative and insightful. Thank you for your attention. Before we conclude, I would like to take a moment to thank you all for your participation and attention throughout this lecture. Take care and have a great day. Thank you all.